All right. We are going to look at chapter 6, velocity analysis, and we're going to continue on where we left off. This is the second lecture in kind of a two-part series, if you would. So the last time we were together, we looked at the first part of the chapter, and now we're going to be looking at the second half. The first half was dedicated to looking at velocities and just velocities on links that would rotate about a fixed center. Okay, ready. Thank you, Jason. And now what we're going to do is we're going to be looking at relative velocity, and that is going to be the second part that we're going to be looking at here. And then what that really has to do with is when we have those 4-bar mechanisms, we're going to find out that velocities of, for instance, outputs are going to rely on the inputs, and we can't calculate them directly like we were when it was one single link. Now, because we've got a linkage and a mechanism, we've got to take into consideration those other things and other links. So that's the focus here. Now, we are going to only be worrying about and doing these problems in a graphical sense. So we'll be using AutoCAD as our tool, continue to use AutoCAD as our tool to draw the kinematic diagrams when needed, and then also to use the vector diagrams in order to calculate any unknown velocities that we're going to be looking at. Now, the vector equation that we're going to be using that kind of ties everything together for relative velocity is going to be the one that we see here. And it's in its very generic sense. So the base vector equation says, when I want to find out the velocity of an unknown value, okay, it's going to be equal to the velocity of something I already know, okay, plus vectorially a relative velocity of the unknown velocity to the known velocity. I know it's very cryptic right now, but as we set this up in our handout and we start looking at a 4-bar mechanism, we'll kind of make sense of this, but this is the base. Additionally, we want to remind ourselves that if we end up needing to determine the angular velocity of any single link, we can use a known velocity on that link divided by its distance away from its center of rotation or its radius. We used this the last time we were together. So it's that W, or lowercase omega, is equal to the velocity, straight line velocity of a point on that link divided by how far it is from the center of rotation. Okay, so that's going to be something that's going to come up as well for us, that equation. So if we look at points that are in pure rotation or pure translation. So number one, we need to determine, this is kind of the process we're going to be going through. We need to determine what the rotation is of an unknown velocity. Meaning if we're trying to find an unknown velocity, at least we very most likely will always know what is the direction that link is going to be rotating in. So that gives us a hint of the direction of the velocity that we'd be looking for. So many times we know directions of velocities because we know that they're always going to go in the direction of rotation and perpendicular back to its center of rotation. Okay. So, so we always usually know at least direction, but it's going to be magnitude that we need the help with. Then you also want to determine the direction of the relative velocities between the two joints, okay? This means that if there is a link that's connecting between the two velocities that we're looking for, that's called our relative link. That's usually going to be our link number 3, or the connecting rod that we've been seeing on 4-bar mechanisms, okay? Then we're going to use that relative velocity equation, and we're going to draw out the vector polygon. We've done this. Okay, that was chapter 3 stuff, kind of preparing us for exactly this. So we'll be looking at that process, and then we're going to measure the vector for the unknown magnitude of the velocity that we're looking for. Okay, and then ultimately sometimes we may need to then say, oh, and how fast is that rotating that link, and then we'll use that velocity as well. So we'll kind of see if that's going to be applicable. So what we're going to do is we're now going to open up and we're going to go to page 7 in our handout to kind of guide us through some examples that will, help us with this. So I'm going to go underneath my camera, and we're going to be on page 7 of 10. So there's 10 pages in here. We're going to be on page 7. And this is where the relative velocity portion starts for us, okay? I want to have my calculator handy as well. All right, so you'll notice up at the top here, it says relative velocity. Relative velocity is going to be used when we need to find out the velocity of a point, but it relies on the velocity of other points or links that are in our case, we're going to be focusing on 4-bar mechanisms, okay? So for instance, when we have a typical 4-bar mechanism here, so number 1 will always be our frame. Number 2 is going to be the crank input. It's going to usually have, you know, some known quantity about it. Maybe it's connected to a motor that's rotating at blah, blah, blah RPMs, okay? And we'll also have distances. Then number 3 is going to be that connecting rod. Number 4 would be like an output or an oscillating output link, okay? Or going around in a full circle, depending on the arrangement we have. Now, we know that when we look at the relationship between straight line velocity of a point on a rotating link, this is going to be the base equation for us. So velocity is going to be equal to W times R. So if I'm looking at the velocity of point B, the velocity of point B is on link 2. Now, you could say it's on link 3 as well, but it is rotating about a fixed center, okay? That is attached because it's attached to link number 2. So link number 2 is going in a clockwise direction around the fixed center A. Now, it's W2, the rotational speed of link number 2 is going to be something most often in a problem that will be given to us in terms of RPMs. But when we want to calculate the magnitude of the velocity here of point B, straight line velocity, we know that this has to be in radians per second. So if we're given the speed of that link in RPMs, we have to do some converting, okay? So that's going to be in here. This was from our part 1 of this lecture, of this chapter. And then the radius is simply how long that is. Or if we look at point B, what's its radius back to, the length back to its center of rotation. Okay. All right. Now, as we look at the relative velocity equation, in this case, for instance, a very common problem will be, we know like how fast our crank is going. We know the lengths of these links. So now what we want to know is, what is the angular velocity, for instance, of link number 4, okay? Very common problem that you're going to come about. So if this is going 1500 RPMs, how fast is that going with, you know, a little bit more information between as far as distances and such, okay? To get at that, we then also need to know, because if we use this, we could say, all right, W4 is going to be equal to, and we know that it's going to be a velocity divided by a radius. Now, when we look at link number 4 is a rigid link that is only rotating about a fixed center. And a point along that link, or at the end point over here, is point C. So what we want to find out is, what is the velocity of point C, because that's the point that's going to pull B along, okay? Or it's going to be pushed, if you would, by B, because B is our crank, okay? The relative link between link number 2 and link number 4 is link number 3. It's the connecting rod. It's the one that is going to be relative, if you would, to both, okay? So in this case, if we expand this out, we're going to say, okay, the angular velocity of number 4 is going to be equal to the velocity of point C divided by the radius of C back to its center of rotation, okay? So before I can find this, I first need to find this, right? I first need to find that. So velocity of C is completely unknown. So we would say the velocity of C, which is completely unknown, this goes back to that generic version of our relative velocity equation. If we go back over here, for instance, okay, we can say that the velocity of the unknown is equal to a known velocity plus vectorially a velocity that is the unknown relative to the known, okay? So to put this in terms of the variables that we have underneath in our example here, we would say that the velocity of point C, unknown, is going to be equal to the velocity of B. It'll be known because we would know how fast that crank is going and how long this would be. Plus vectorially, the velocity of C, which is unknown, relative to B, which is the known. Now, if you recall from the last time that we were together, our straight line velocities are a component of rotation. And they are always, starts with a P, to its center of rotation. Do you remember? They are always directed perpendicular. Velocities are always perpendicular to something, okay? So if I have velocity C, and I want to determine what its direction is, notice that it can only rotate about a fixed center here, right? And if we know that it's going to be rotating in a clockwise direction, do you see how the velocity of C is going to be directed to the right and up and perpendicular to that link? Okay, always. So we know direction. We know direction, and we should probably put it like in a, you know, a direction, something like that, because we don't know its magnitude, but we do know its direction. With B, and assuming, I'm actually going to give it a number. We're going to give it 1500 RPM is going to be W2. And we're going to say that the length, if you would, of crank 2 here, link number 2, how long do we want that to be? You tell me. We'll make up the problem as we go, but we'll do it. Sure, 6 inches. 6 inches. Okay. And then let's fill in a couple other dimensions. How long do we want the connecting rod number 3 to be? If that's 6 inches, how long should link number 3 be? Let's go proportional to what we have. 5, that looks good. I like that number better. Not that 18 is not great, but let's go a little proportional to what we have, okay? And then we're probably going to know an overall length of link number 4 as well. How long do we want that one to be? Thinking and looking proportional. Sure, let's do 4 inches. That sounds good. Okay. So with this information, all right, we know the direction of C, but we don't know its magnitude. So underneath here, I always, or even on the top, it doesn't really matter. I like to kind of check off. Remember, velocities require 2 quantities to fully define them, magnitude and direction. So we don't know magnitude, but we do know direction of our velocity C, right? We know that it's going to be on a line perpendicular to link number 4. So we'll be able to, you know, kind of put that in. Velocity B, we actually know magnitude and direction. And the reason we know magnitude and direction, and we'll actually calculate it, is we can find, and we know what W2 is, we'll have to convert it to radians per second. And we also need to know, we also know how far away from the center of rotation it is. It's 6 inches. So we'll be able to calculate that magnitude. And we know its direction. What is its direction? Down and to the left or up and to the right? Or down and to the right or up and to the left? Why do you say down and to the right? That's correct. Yep, it's in the direction of rotation, and it needs to be what? Perpendicular to the length of the radius back to the center of rotation. So here is where, here is where the velocity of B is going to be. It's perpendicular to this, right? Perpendicular to that. Okay. So we know both magnitude and direction there. Now, the velocity of point C relative to point B. The velocity of C relative to point B. The velocity of C relative to point B is the straight line velocity component of link number 3, because that's the link that connects those two. Okay, that's the link that's between those 2 points. Now, what we are going to do is, and I always draw this as a dotted line because I really don't know which direction this is going to go in. but it's perpendicular to the link or the line connecting the 2 points that we're interested in, or that we know about. So we know B and we're trying to find C. This is the line or the link that connects those two. So this is going to be the velocity of C relative to B. Okay, only know direction. So here as well, we don't know magnitude, but we do know direction. Now, as we look at this vector equation, notice that we have two unknowns, right? Remember back from chapter 3. Are we worried about that? No. They're also, you'll notice, separated by the equal sign. So that's exactly how we want those to be, okay? We have two unknowns, and we have one unknown on the left-hand side of the equal sign and one on the right hand of the equal sign. So this is perfect. That way we can find an intersection, and then we can determine the magnitudes of the two quantities that we need, okay? All right, so now what we want to do is we are going to kind of solve this, all right? So what is the process? And we're going to look process only right now and sketching the values out. Okay, sketching the values out. I'm going to stay away from AutoCAD from right now because it just introduces another thing. Okay, I'm not worried so much about everything being perfect and that the values are accurate. I want to show you the process first. Okay, so as we look at our vector equation here, we will notice that where we know everything and where we can calculate is going to be at our velocity of B. So we want to figure out what is the magnitude of B. So I'm just going to, I do have a second side here. So what I'm going to do, I'm going to use a piece of paper here. I'm going to grab it out. And number one, we're going to calculate that magnitude of velocity B. So we are going to use this equation right here. This is going to be like I should take that back. Our first step will always be the diagram, okay? Because we're going to need the diagram to be able to create our vector equation in a little bit, all right, because of the perpendiculars. So step number one is always going to be your kinematic diagram. Step number two then is going to be to calculate anything that we know, okay? So this is step number two, and this is going to be the velocity of B is going to be equal to the angular velocity of link number 2 times the radius to point B, which would be the length or the radius of link number 2. Okay, now the W we know has to be in radians per second. So our W2 is equal to 1500 revolutions per minute. We need to convert that to radians per second. Okay, that's step number one. So we know that there is 2 pi radians in 1 revolution. Since revolutions is on the top, remember, you have to expand it out. You can't write it as RPMs. You have to put revolutions and then minutes on the bottom as a fraction. So if revolutions are on the top here, I need to convert it to radians. Revolutions are going to go on the bottom, so that when I multiply across the top, divide by the bottom, these two cancel. And I'm left with radians on the top. Now you'll notice I'm in radians per minute. So what I need to do is I need to convert my minutes to seconds. Okay, so minutes are in the bottom here. So that means 1 minute is going to go on the top, 60 seconds underneath. Now minutes is going to cancel, and I'm left with uncrossed out radians per second, right? Radians per second. So that looks good. So now I need to find my value. 1500 times 2 times pi divided by 60. Oh no. Yeah. An equation. Hold on. The setting got reset on here and I don't know how to get it off. Oh, here, equation. Now it's off. Okay, good. Sorry. What did we get for a number? You guys should be doing these with me. $157.01. I get 0.08, or maybe 157.1. Anybody else? Everybody else get that number? Make sure you're doing it along with me, because you'll have to do this by yourself. This is good practice to be sure that your answers come out. Now, my units are going to be in radians per second, right? Radians per second. So now I'm going to take that number and we're going to put it over into our equation to solve for the velocity of B. So velocity of B is going to be 157.08 radians per second. Now, when you write this out, resist the urge to put this as a slash and put it in line. Put radians on top, seconds on the bottom, so that you can definitively know what your final units are. You know, what's in the denominator, what's in the numerator. Times the radius or the length of that crank, that link number 2, and that's going to be 6 inches. Okay, 6 inches. So we're going to take our 157.08 times 6, and that is going to be the magnitude of the velocity of B. What do we get? Sure. 942 point, I get 48. Yeah, it's a 7 repeating, right? And what are my units? Inches per second. What happened to the radians? The Lucky Charms, they magically disappear, right? Yes, they magically disappear. So whenever we multiply radians by something, it's unitless, essentially. It just drops out, right? And so we now just have inches per second. There's nothing, there's no such thing as a radian inch per second. It's just inches per second. Okay, now this is our magnitude, right? This is our magnitude of B. And as we look at our diagram up here, we know its direction as well, you know, based on the angle, if you would, that link is on. Okay. So let's go back to our vector diagram. So our vector diagram, we know both magnitude and direction for B. We know direction only for C plus or C relative to B, and then we're going to have to find also, knowing its direction, its magnitude for the velocity of C. So we're going to draw our vector diagram now. So number 2, or I should say number 3, step number 3, and I'll put step number 3 over here. It's going to be that vector diagram. Okay, vector diagram. So the vector diagram is going to be the velocity of, C. It's going to be equal to our B plus factorially C relative to B. And again, this is unknown is equal to known plus the relative velocity of the unknown to the known. So it's exactly in this format. To put B relative to C is incorrect. It's incorrect because B is our known value. Our C has to be relative to something that's known. So it has to be C/B, if you would. Okay. So the order makes a difference here. Now, as we look at this equation, as we have already pointed out, we know everything about velocity of B. That's where we want to start. We also know that the equal sign is also our origin in this equation, just like what we practice in our chapter 3 stuff. Okay. So we're going to draw, I gotta look at my vectors here. I think it's gonna go something like this. I'm gonna put my origin here. We're sketching now, sketching process. So we're not gonna get too, bogged down in the details and the accuracy. We're gonna just do our best. We're gonna sketch the process. And what we're gonna do is we're gonna take this velocity of B in the direction that it is, perpendicular to the link. So if I had this drawn in CAD and I wanted to find out what that angle was, I would simply draw a line perpendicular to it. And that's the line of action of the velocity of B, okay? You can imagine doing that. So I'm just gonna draw it right now. So it's gonna go down and to the right, and it needs to be 942 inches per second long. We'll identify that. So I'm gonna go something like this. See, I'll go like this. velocity of B. Okay. And I'm going to call it, there's my velocity of B. Okay. So imagine this would be link number 2, and this is perpendicular to it. Okay. That's how we get its direction. Now, as we look at this vector equation, we're going to add vectorially to it then the velocity of C relative to B. The velocity of C relative to B. Now let's look back up here. The direction of C relative to B is along this line perpendicular to the link connecting points B and C. Okay, that's a horizontal link. So that means that on the tip, because I'm adding vectorially on the tip of the velocity of B, I am simply going to draw a vertical line. Okay, this is velocity of B rather than on the endpoint. This is a vertical line representing the direction only of the velocity of C relative to B. Okay. Any questions so far? So when I look at this equation, I've done everything I can on the right-hand side, right? So now I'm going to cross back over the equal sign, which means I'm going back to my origin, and I'm going to start the tail of the velocity of C. Okay, let's look what we have. We know that C is going to be on a line perpendicular to link number 4, but we don't know how long it's going to be, right? Okay, so what we're gonna do is we're just going to draw a line through the origin that is going to represent the line of action of velocity of C. See that? And again, that is perpendicular to link number 4. So when we have it drawn in CAD, we're going to go perpendicular to that link, and that's going to be its line of action. We will do a couple CAD involved processes, so you'll see that too. Okay. All right, now we have an intersection. This is what we want, but we have to be careful of arrowheads, okay? So recall that when we add two vectors together, so velocity of B plus vectorially C relative to B, that means it's always tip to tail. So on the tip of B is going to start the tail of the velocity, okay? And then the arrowhead is going to go to the intersection that we just created, okay? And that's going to be my velocity of C relative to B. And if I wanted the magnitude or needed the magnitude, I would simply measure it in CAD. Now, velocity of C. Velocity of C, I cross over that equal sign. That means that my tail is going to start at the origin, and its tip is going to go to the end of the right-hand side of the equation. So its tip is going to go to the right, which makes sense to us as we look at the direction of the way this is going. If our driver is rotating in a clockwise direction, just kind of the way this looks, this is also going to want to go clockwise, right? And that means that being perpendicular to that link, velocity C is going to go up and to the right. So check those things out to make sure that it all makes sense. Okay, so the direction here indeed does make sense. So now I can measure for the length of that vector. Okay, for the length of that vector. And I would use AutoCAD to do that, because then I would get the most accurate result. Now, once I have that velocity, remember, my problem that I kind of stated to you guys was, I really want to know, what is the angular velocity of link number 4? But I had to get, velocity of C here, right? So my step number 4 here now is, now that I can measure for the magnitude of the velocity of C, and I know that its radius is 4, now I can calculate the angular velocity of that entire link. You see that? Okay. So my step number 4 now is going to be W4 is equal to velocity of C divided by the radius or the distance or the length of link number 4. Okay. Which means that this number right here is going to come from there, right? And that's going to be in inches. Make enough room here. That is going to be in inches per second. Okay. How do I know that's in inches per second? How do I know? Exactly. Velocity of B was in inches per second, and I used that, right? So all of these have to have the same units. So yes, that's going to be in inches per second, whatever that number is. Okay. And again, you would get that from your CAD diagram divided by, and this is going to be 4 inches was the number that we used for the length of that length, the length of that link. Now, as we look here, units are going to cancel. Inches and inches are going to cancel, and there's going to be nothing per second, right? There's going to be nothing per second. It's going to be like this, and it's going to be something per second. Or is there something on top? Yes, yes. Radians per second. Remember, radians are unitless, and they magically appear when there's nothing there. When we're dealing with problems that we have this rotation and linear stuff, they magically appear. Okay. So now this is going to be a number if we don't know what it is right now because we don't have the magnitude of C. Okay. Now, when you are given a problem like this and you're like, okay, I have the rotational speed of link number 4, and my answer out of the equation comes out to be radians per second. You are not stopping there. What are you going to do as a very final step? So if I wanted, if somebody was asking, what is the rotational speed of link number 4? Are you going to say, oh, it's 14.7 radians per second? No, you're not, Eric. No, not a distance and an angle. What would we want to switch it to? Remember what we did last time? Oh, look in the handout. I think we did some of these types of problems in the handout oh yeah, look on page number 2. Change it to RPMs. Exactly. So that's what we want to do. We want to then finish up with, and again, this is process only. We're not going to get any numbers here. We want to finish up with, we want to change this to RPMs or revolutions per minute. So we would say 2 pi radians, 1 revolution, and then we would have 60 seconds on top in 1 minute. So then my seconds cancel, radians cancel, and I'm in revolutions per minute. So my W2 would officially be a number in RPMs, right? After we do that conversion, okay? After we do that conversion. Now, is that rotational speed fully defined by a number and its units? If I look up here. Oh, I'm sorry. You're on the wrong page. Get back to page 7. If I look up here, is there anything else I may want to add to the answer? So if I confirm that this is the direction it's going in and I hold this, and I have its magnitude in RPMs, what else do I want to add here? I'm going to actually erase this. Exactly. You want to put in that this is going clockwise or counterclockwise, whatever that would be. And that would fully define it. Fully define it. Let's see, there's a message up here. So radians comes back when there's an absence of other units. Correct. When we are in this mode of rotational motion relating linear and rotational velocities. Does that make sense, Jason? Yes. They magically appear. That's why, to help you to kind of remember that. So if nothing is left, then radians pop in. Yes. Good. Okay. So this is the process of a problem like that. Let's review the steps. Step number 1. Step number 1, kinematic diagram. First and foremost, we draw it in the arrangement that it's in. So that was that chapter 1 stuff, chapter 1 and 4 when we were looking at that, right? Drawing the kinematic diagrams. Step number 2 is going to be identify, and it's usually on the crank, not always. Some of these problems will switch around a little bit, but you want to kind of find out what you already know. And many times we're going to know how fast the crank is going, and we want to know what's happening on the output, okay? So then we want to determine any magnitudes that we can get. Then we're going to write our vector equation that relates our unknowns to our knowns to our unknown to known relative velocities, okay? And then we're going to do that vector equation. So that's this stuff right here based on the directions that are given to us in the problem and then also from our original diagram, okay? Those perpendiculars are going to be really important. And then finally, if needed, we're going to use any magnitudes that we grab to then finish kind of the problem. In this case, we wanted to know what was the rotational speed of that final link, W4, and we needed to get the velocity of C first. So we had to measure that off of our vector diagram and then use it to get our final answer. We didn't really get a number, but we know that we would be, you know, starting with that magnitude of velocity of C. Okay, so any questions kind of right now in that relative velocity like process? All right, don't know what to ask, right? Don't know what to ask. We need a little bit more practice. So let's do an example like this, and I'm going to walk you through the process before we look at a slider crank mechanism. So we're going to go back to our book and we're going to look specifically at example problem 6.6. Example problem 6.6. It is a familiar mechanism to us. We're going to be looking at that rock crusher, okay? And here we have our rock crusher. It gives us all the dimensions up here. So at the top of page 131. This is the same type of a diagram that we just looked at, except it's like flipped over, right? So we had our 4-bar mechanism on top of the frame. This time it's underneath. And we've looked at this in detail in I think it was chapter 4, where you looked at kind of putting it in a couple different arrangements. So let's look at the problem statement. It says here in figure 611, which is the rock crushing machine, it's used to get larger rocks placed in a vertical hopper that fall into a crushing chamber. Properly sized aggregate is going to pass then through. So it crushes. The finer stuff goes through, and then the other larger stuff is reintroduced back in until it's completely crushed up. Determine what the angular velocity of the crushing ram is in the shown configuration as the 60 millimeter crank rotates at 120 RPMs clockwise. Okay, so angular velocity of the crushing ram. Here's the mechanism. And as we look here, this is the crushing ram. All right. Now, like I said, we've looked at this one before a couple times. And as we had created our kinematic diagram, you're going to notice it's going to look just like this. Okay. So coming down from the frame, this is the crank. Okay. This is the 60 millimeter crank that they're speaking of. It is going to go in a clockwise direction, and its W2, if you would, is going to be 120 RPM. They add that to the kinematic diagram right down here. Okay. And then link number 4 is going to be our ram. Okay, link number 4 is going to be our ram, right? So what I've done is I already have this drawn. Okay, I already have it drawn. Oops, I gotta get it out of my. So I'm gonna open up AutoCAD and I'm gonna show you then the process. Now, you don't have to do this with me. I don't know at the moment. You'd have to look back. Let me pause the video for a little bit because I'm having to undo my my camera because I only have so many things here. So hold on. I'm gonna pause. All right, so now what we're going to do is we're going to go over to AutoCAD and we are going to look at the kinematic diagram in AutoCAD. And we're going to use it here because you want to draw this first so that now we can use our links to get our directions for our velocities. Okay, so this problem wants to know what is the rotational speed of link number 4. And we know everything, if you would, about link number 2. We know that it's going in 120 RPMs going clockwise. We know the length of this link. If we go back to the illustration, it's 60 millimeters. So we can calculate what the velocity is of the endpoint of that link, which is velocity B. Then it's connected to link number 4, which is where we want to get our rotational speed of link number 4. And on the endpoint of link number 4 is point C. So we need to find out what is the velocity of point C. Okay, so what I'm going to do right now is I'm going to add in, if this is going at a rotation here, we're going to put the velocity vector in here perpendicular to link number 2. So I'm gonna actually move this link number 2 thing, and I'm simply going to put in a line, and I'll use the object layer line, and I just want my line to be perpendicular to it. Now it's vertical, so I can use my ortho mode, and I can just simply draw a line from the center, the endpoint of that perpendicular to. I'm not going to worry so much right now about arrowheads because I have to find its magnitude in just a second. Then what I'm going to do is I'm going to do the very same thing here. I'm going to draw a line through point C that's going to be perpendicular to link number 4. So to do that, I'm going to grab my line and I'm just going to do an endpoint anywhere out here. And I need to turn off my ortho because it's not horizontal or vertical. And I just want to do a shift right mouse button and go perpendicular to link number 4. And now I have a line that is perpendicular to that link. I'm going to put it out at the endpoint where C is. So I'm simply going to do a move. I use M, and then I'm just going to go to intersection there. There we go. Okay, so now I've got the perpendicular line of action of velocity of C. The last perpendicularity that I need is going to be the perpendicular line of the velocity that is C relative to B, and it's going to be perpendicular to link number 3. So I'm going to do a line. I'm just going to start out here, and I'm going to go perpendicular here. Okay. Now you could change colors if you wanted to. I'm just going to leave them white for right now, and I'll add my labels as we go along. But let's go back to our process and kind of see where we're at. So actually, here, this one. So if you remember from the last problem that we did, we drew our kinematic diagram. I'm sorry. We drew our kinematic diagram first. Then we kind of put our labels for our directions, which we just did in the CAD. Now we're ready to calculate that velocity of B. We can calculate the velocity of B, its magnitude, because we know its angular velocity of that link and the length of that crank. But we have to use the numbers from our problem. So the length of that crank is 60 millimeters. And the rotational speed is 120 RPM. So on, never enough room. Okay, so step number 1 was our diagram. And on the diagram, make sure that you add your labels and then any perpendiculars, I'll call them, okay, which we just did. So step number 2 now is going to be the velocity of B is going to be equal to W2 times the radius of 2. So we're using that very same process that we did last time. Okay. And here we know that our W2 is 120 RPMs, but we can't use that. So we need to convert that first. So I'm going to just kind of over here on the side, I'm going to take 120 revolutions per minute. And I need to convert that to radians per second. Okay. So 1 revolution on the bottom here is 2 pi radians on top. Revolutions cancel. I'm in radians per minute. And then I'm going to do 1 minute is equal to 60 seconds. Minutes cancel. I'm in radians per minute, or I'm sorry, radians per second. So my W2 will be, I grab my calculator. What do we get? $12.57 units. Radians per second, right? Radians per second. Anybody, did everybody get 12.57? I don't know. I don't have it. I don't have it in front of me. Okay, so now that's going to be the number that we use over here, right? We're not going to use the RPMs. So my velocity at B is going to be equal to 12.57 radians per second times the radius or the distance of that crank. So that was 60 millimeters, right? So my velocity at B, what's my number? And units. Everybody should be doing it. Calculators out. If your hands are folded and you're not doing it, then you're giving me an answer. I can't hear you. Confirmed. Anybody else get that same number? 753.98 millimeters per second. I got 1 thumbs up. Okay. Everybody get it? Virtually too? You guys good? Okay, cool. All right. All right, now that's not a final answer, but that's the magnitude of the one known value that we need in our vector equation. So that's our step number 3. We need to go back to here. We have to determine what the velocity of C is, knowing everything about B, and then passing through our connecting rod, which is the C relative to B. So velocity of C is going to be equal to the velocity of B plus vectorially the velocity of C relative to B. Okay. Now, as we look here, let's evaluate. We don't know the magnitude of velocity of C, but we do know its direction. We know its direction because C is on this link that can only rotate about a fixed center, and it is going to be perpendicular to that link at this instant in time, which we already drew in CAD. Okay, so we'll go over there in just a minute. So we know direction, but we don't know magnitude. Velocity of B, we just got its magnitude, and we also know its direction because right here, it is on link number 2, and we know that it is going in a clockwise direction, so it's going to point to the left, and it's going to be exactly 753.98 millimeters per second. Okay, so we know both magnitude and direction there. And then velocity of C relative to B. That's the velocity of this link right here. We don't know its magnitude, but we do know direction again. We do know that it is perpendicular to that link connecting C to B. So we go like this, we go like that. Okay, so we don't know magnitude, but we do know direction. So as we look at it here, are we okay to start drawing a vector diagram as we see it here with 2 unknowns? Yes, yes, we saw it before. So what I want you to do is sketch it down here first. Just sketch what you think it's going to look like about the directions, you know, kind of what we looked at. So if you look at this diagram here and you think about perpendicularities and directions, what should this look at? Don't look over here. I just want to kind of go through the process first and make sure we understand why we see the things the way we do. It's one thing to look at an example like, oh, yeah, I get it. But make sure that you really understand the way that things are written out there and that it makes true sense. So as I look at this, I'm gonna look at my two sides of my equal sign. My equal sign, you know, is my origin, right? I always start at my origin. And I start on the side where I know the most amount, which is going to be my velocity of B. So I just drew to the left the velocity of B at a length. Okay, I'm not like scaling this out right now. I'm sketching the process. Okay, so my velocity of B, I chose to go to the left. Why did I do that? Because the rotation of link number 2, that velocity of B is on, is going in a clockwise direction. So if this were to suddenly stop, B would continue in a straight line going to the left. So that's why its direction would be definitively to the left. Then I'm going to continue on the end point of the velocity of B on the tip. I'm going to add the velocity of C relative to B. I don't know its magnitude, but I do know direction. And I know its direction to be perpendicular to this link right here. So I'm going to draw a line then that's something like this. Okay, I don't know if it's going to intersect up, down, left, right, but this is going to be my velocity of C relative to B. So now I've done everything I can on my right-hand side of the equation, right? Everything is done on the right-hand side of the equation. So now I've got to go to the other side. And I'm going to go back to my origin. So I'm going to start this next vector at that origin, and I need to sketch the line of action of the velocity of C. So if I look back at my diagram, C is right here. So it's going to be perpendicular this way, right? Perpendicular that way. So starting at the origin here, I think I can do it. There we go. Something like that. Velocity of C. Okay. This line of action is perpendicular to its length that can only rotate about a fixed center. Okay. Questions so far? Now what I want you to do, if there's no questions, draw in the arrowheads. Draw in each one of the vectors for the velocity of C relative to B and the velocity of C. Darken them in and put your arrowheads on. Finishing up the right-hand side, the velocity of C relative to B, its tail is going to start at the tip of B because we're adding these together. So that means at that intersection that's created, my tip is going to go to it. And then because I cross over the equal sign, the tail of C starts back at my origin, and its tip is going to go to the tip of the last vector on the right-hand side of the equation. Okay. Now, that's velocity of C. Let's put it in CAD now. Okay, so that's what it's supposed to look like. It looks like it matches on the illustration. So let's go over here. So right now we have the lines of action of each one of the individual vectors. So I'm going to start by creating, and I'm going to do this over on this side here-ish. Okay, creating an origin, just like we did when we were in chapter 3. I have to know where you're starting. Okay, I have to know where you're starting. So you have to identify an origin first. So now what I'm going to do is I am going to do, let me see here. This one was, I think I might have to go a little bit further to the right and move that. Okay, so I'm going to draw I'm going to move this vector line of action from my endpoint done. I'm going to go to this intersection. That's where it's going to start. And I'm simply going to make it, what was my number? What was my magnitude of the velocity of B? $753.98. There we go. And I want it from here to there. Okay, so now I'm going to extend my line right there. Okay, and on its endpoint, I am going to draw my arrowheads. So I'm just going to draw them in line form, not in leader line form. Okay, so this is my velocity of B. And I'm going to take this. I'm going to go here. I'm going to label it. I just did a copy on that, and I'm going to simply call this VB. Enter. That's it. Okay, and it's pointing to the left. I don't have to put the dimension on because when you get your final answer, if you get it right, then I know you did it right, but it's going to add, just like we did in chapter 3, more details, and it's going to get cluttered. So there's my velocity of B fully defined. Okay, now on the endpoint of B, I am going to put the line of action of C relative to B, right? So I know, I'm going to move this a little bit further to the left, maybe down here. I'm going to take this line of action. I'm going to move this. This is the velocity of C relative to B, right there. Okay. And then I'm going to add, with its tail is going to be the velocity of C. So I'm going to move this vector. Notice that I only use my diagram to get the directions that I need for my vectors. Okay. Now I need to find the point of intersection. I can see, and we already kind of sketched it out. We know it's going to be like right around in here, right? So one of the functions that you have in AutoCAD is the fillet function. And depending on if you changed it or anything, but coming in as a default into AutoCAD, your fillet function will have its radius set at 0. So it'll make like a sharp corner and it'll trim things off. So I'm going to use that fillet function. Now the fillet can either be found up here in the modify area, or you can just type it in. That's what I end up doing a lot. So that's there and there. Oopsie. Come on. There. Okay. And now you'll notice that when I'm here, it creates not a rounded edge, but a sharp corner because it's a radius of 0. Okay. Now I need to finish it with my arrowheads. Okay. And labels. So, so I'm going to add in line for the velocity of C here and here. I'm going to make this one a little bit bigger just so we can see kind of the difference. And then I'm going to copy this up here and over here, and I'm going to label them appropriately. This is the velocity of C. And this is the velocity of C relative to B. Okay, so make sure you have them labeled. The only one that we need a magnitude on, we already know its direction based on our diagram. We only need its magnitude is going to be the velocity of C, because I need that for the rotational speed of link number 4. So we're going to go into an aligned dimension. Okay, from that endpoint to that endpoint. Now it's pretty small. It's pretty small. So I'm going to have to go into annotate. I'm going to go over here. And I just need it big enough. I don't need it super perfect. Ugh, this is an ISO. Yuck. I shouldn't really worry about this. I just need to go to fit. And I'm going to say, I don't know, let's do 15. Let's say okay, because it's kind of small. Set as current, close. Ooh, that's really big, but that's okay. Now, what was our number when we found, oh, we didn't yet, right? We were using this. I'm sorry, we didn't, but we can compare it to the book. What did they get for their number? Looks like they got 784. If you look on page 131, the only thing I can guess is it looks like they probably they rounded their velocity of B. They didn't use it to the decimal point. So it's going to be different than ours, which is okay. Ours is better. Ours is more accurate. So if I go on here, I'm just going to put this on my notes layer. So it's the same. Okay. Now this tells me what the velocity of C is. Okay. This is its magnitude. Now, if we go back to our problem underneath here and we look at the problem statement, they want us to determine the angular velocity of the crushing ram. Okay. This is a straight line velocity of C. Okay. Remember, the velocity of C is out here. So it's in that direction, right? We now know it's straight line velocity. How are we going to get the angular velocity of link number 4, W4? If you look back at the previous example we did our vector diagram, and then we need to do the angular velocity equation, rearranging it to solve for W4 using the magnitude of the velocity at C divided by its distance. So our next part, we're not done yet. The next part of this problem is going to be using the velocity of C. We're gonna calculate the angular velocity of 4. It's going to be the velocity of C divided by that radius of 4. Okay. So go ahead and plug in your values. So you'll notice I'm going to use the one off of our AutoCAD here for the velocity of C, since we've been using more accurate numbers than what the book is. So our velocity of C will be 789.88 millimeters per second. Now the metric system, as a part of their standard, will use, instead of a decimal point for its decimals, it'll use a comma. So that's why that's there in the number for the dimension. Divided by the radius back to its center of rotation. So now we need to look at the illustration. The illustration said that this is 180 millimeters. That's going to be our R4. Okay. Millimeters cancel out. What is the magnitude of the angular velocity? Say it again. 4.38. What are the units? Radians per second. Yes, because millimeters canceled out. So there was nothing per second, right? So radians magically appear for us. So now what do we need to do with this number? 4.38 radians per second. We need to do what? Convert it to RPMs correctly. So our 4.38 radians per second, go ahead and convert it to revolutions per minute. What's the number you get? And that's going to be revolutions per minute, or RPMs. You can write it in that as well. Okay. So if we turn the page, the final answer should be there. They left it at 4.36, but we won't. Okay. Oh, additionally, we do need to add the clockwise, counterclockwise. So they got clockwise. So you'll notice that if our velocity, as we confirmed in our vector diagram, is going up and to the left, then this will indeed be going in a clockwise direction. So that would be our W4. Okay, so we do want to add that to our answer, but we do want to have it in revolutions per minute. So this would be clockwise. Add that on for the direction as well. Okay.
They did 2 links in this example.
They ended up doing, I think what they did was the angular velocity of link number 4, which was what the problem asked for. And I'm not sure why they ended up doing the velocity, the angular velocity of link number 3. That is kind of insignificant in terms of the problem itself. We're usually interested in just the input and the output. That other one, again, is kind of like it's just the connector, okay? There isn't very many instances where we want to know what the actual straight line velocity of that link is, because it's kind of like oblonging as it goes. It's not rotating about a fixed center. So it's kind of like a weird little one in there. So at that instant in time, its angular velocity is that, but there is no fixed center of rotation that it's rotating about. So I just stuck with, they only asked for in the problem, what is the angular velocity of that output link, which was number 4. Okay. Any questions so far? So we kind of saw this process twice, very same process, a little bit different problems just in its configuration, but the application, again, the steps were, we first do our diagram, put your labels on, and then determine your perpendicularities for those directions of velocities, okay? We then are going to find out or determine the magnitudes of any velocities that we actually, know. So on the crank side of this one, we could calculate what that velocity of B was based on the rotational speed of the crank and its distance from its center of rotation. Remembering that in and out of this equation, W has to be in radians per second. So our input speed was given to us in RPM, so we had to convert that first. Then once we knew that magnitude, we could then go to our relative velocity vector equation and setting it up in the way that we did before. Velocity of C, which is our unknown, is going to be equal to the velocity of B, which is known fully, magnitude and direction, plus vectorially the velocity of the link that is the unknown C relative to the known B. Okay, so C relative to B, which is simply perpendicular to the connecting rod. So then we went and we drew that kinematic diagram. I had it drawn in CAD here to get our orientations at this instant in time. Perpendiculars to each one of the appropriate links. VB perpendicular to link number 2. VC relative to B perpendicular to link number 3. And then VC, the velocity of C, perpendicular to link number 4. Okay. And then using those orientations and the order of the addition, the vector addition here, we then laid out and got the magnitude of the velocity at C. Okay. Once we had the velocity of C, we then could calculate the rotational speed of link number 4. And that's what we did in our final step, using and rearranging that base equation relating the straight line velocities and angular velocities. W4 is equal to the velocity of C divided by that distance that C is away from the center of rotation. Okay. And then converting it into RPMs and identifying the rotation angle, if you would. Okay. Or the direction of rotation, clockwise in this case. Okay. So this is a 4-bar mechanism process that is using a crank input and an oscillating output. Right. Let's look at our handout again. Let's go back to our handout again and see where we're at. Out of the way. So we did relative velocity here. Okay. 4-bar crank rocker type of a mechanism. Okay. And we did our first example was just process only, but then our first example with numbers was the same type of a problem that we see here. Okay. Now turning the page, the other type of mechanism that we've seen on a regular basis is our slider crank mechanism, okay? And that's where, as we know something about the input is our crank side, the output is going to be a slider that can only go in a linear fashion, okay? It's not oscillating out there, right? So if we wanted to know, for instance, what's going on at link number 4, the only thing that link number 4 has is linear motion. There is not a rotational component there, okay? There is on link number 2, because link number 2 can only rotate about the fixed center A, okay? It has to rotate, connecting rod back to our slider, but our slider can only move along this line of action back and forth, okay? Back and forth. So it only has linear velocity, okay? So what we want to do is we want to look at problems like this, because those are also common 4-bar mechanisms, to be sure that we can solve for those. So in this case, here's another relative velocity problem. We want to find out what is the velocity C relative to or dependent on the velocity of B, assuming that we know everything about the crank. And most often we do. We usually know what is the motor that's connected to it. How long is that crank? How long is the connecting rod? So how fast will this slider be going back and forth or in whatever direction that it's going at this instant in time? So at this instant in time, this is going in a clockwise direction. So what that means is our velocity of B is going to be going up and to the right, right? Velocity of B. Our velocity of C relative to B is going to be going perpendicular to the link connecting C and B. So this is going to be the direction. We really don't know which way yet. We'll get that when we do our vector equation, but this is going to be C relative to B. And then at this instant in time, if this is pulling or going in a clockwise direction, we're pretty sure the velocity of C is going to go to the right. Would you agree? At this instant in time? But it can only go in a horizontal direction. All right. So it says here, draw in all the vectors on the diagram, which we just really talked through, right? We know the direction of VB. We know the direction of that relative. And then we also know that the velocity of C, the slider, can only go in a horizontal direction in a linear manner. Okay. So let's look at problem 620. Problem 620, all right, in your book. And problem 620 is located on page 162. Okay, it's right here. All right. Now, the problem that we're going to be looking at is the compressor linkage above, and using the relative velocity method to graphically determine what the linear velocity is of the piston, okay, as that crank rotates in a counterclockwise direction of 1,775 RPMs, okay? So using that description, here is our kinematic diagram, okay? Kinematic diagram. What I want you to do is I want you to show on here first the velocities of B. So show me the velocity of B, C relative to B, and the velocity of C. So go ahead and sketch each one of those on the diagram right now. The way that you think, what the directions would be in representing each one of those vectors on the kinematic diagram. Okay, go ahead and do that. So hopefully as you're looking at the diagram, I penciled mine in here. You should represent very closely what we see here. So as we I always like to start at kind of the start of things, which is going to be our link number 2 here, our crank. We know that it's going at 1775 RPM counterclockwise. So at this instant in time, my straight line velocity component of point B is going to be going down and to the left perpendicular to link number 2. Okay. I also know that my velocity at C is a slider. And as this is rotating in a counterclockwise direction, it's kind of going to be flattening out. So it's pushing that slider to the left, and it can only go in a horizontal direction. The slider can only go horizontally. It's constrained. So that velocity on a slider is not perpendicular to anything. It's along the line of action. That's that rectilinear type of velocity. It is constrained only to be straight line. And then we have the connecting rod that we're going to need to determine the velocity of, or show it in our diagram. And we know its direction is going to be perpendicular to the line connecting B and C. Okay, B and C. And as we kind of skip down to step number 3, here's our familiar equation. If we're trying to find the output velocity of C, we're going to set that equal to the velocity of B, where we know everything, right, on the crank, plus vectorially the velocity of C relative to B. Okay. So before we go down there and start drawing anything, we need to first determine what is the magnitude of velocity of B. And we have everything there. So go ahead and solve for the velocity of B. All right, so you should have, and I'll just kind of put a little cloud around this because it's not a final answer, but here is the magnitude of the velocity of point B. Did you get 371.7 inches per second? Everybody get that? Yes, no? Okay, I've got nodding. So you first have to convert your revolutions per minute to radians per second. We have to use then the 185.9 radians per second here, and then multiply by the radius of 2, which is the length of link number 2. Any questions about this at all? Okay. So this is the magnitude now. So this is the magnitude of the velocity of B. Okay. So I did draw diagram here of this problem in AutoCAD. So let's see how we would continue on in AutoCAD. So if we go to here, here is our kinematic diagram. Very same thing that we saw in the book, same links, you know, all of that. And now what I'm going to do is I'm going to add in, and I'll use 0, the lines that are going to represent the lines of action of each one of our vectors. So I'm going to start by, none of these are well, the only one that's horizontal is going to be my velocity at C. So I've got my ortho on. So the velocity of C is going to be a horizontal line because it's constrained horizontally. Then I'm going to do a line out here, and then I'm going to go perpendicular to number 2. So I'm going to move this to the endpoint. Okay, so that's the line of action for the velocity of B. And then I need one more line of action, and that is going to be of the velocity of C relative to B. And that's going to be perpendicular to the link connecting B and C. All right, so my velocity is pretty big. So what I think I'm going to do, this right here is only 2 inches long, if I remember right. Yeah, it's only 2 inches long. So if I would draw my velocity of B at the full 371, it's going to be like huge, right? Compared to this. So what I am going to do is, as we look underneath here, I'm going to divide this by 100. So I'm going to move this decimal place 2 places to the left. So I'm going to actually draw my velocity of B 3.71 inches long. So when I get my answer for the velocity of C, I'm going to have to multiply it by 100. Okay, just so you know. And I'm just going to do that so that when I draw it next to my vectors here, these lines aren't like so out of proportion. Okay, so I'm going to start with an origin, just like I normally do. So I'm going to do a vertical, horizontal line, and then line. Nothing super fancy, just to signify that this is where I'm starting with my origin. Now, as we look at our vector equation, here's our origin. We're going to start on the right-hand side because this is where we know both magnitude and direction for B. We know its magnitude and we know that it's perpendicular to. So we're going to move that line of action down to over here. So I'm going to do move here, and it's going to be going down and to the left. Okay. Then on the end point of the velocity of B, I am going to add, oh, I have to do something first. I'm so sorry. Let me get the correct length of B. I have its line of action. I have to get the correct length of B because I do know its magnitude. So from the center here, I'm going to do a radius of 3.7169, which is our velocity divided by 100. Okay. And then I'm going to extend the radius down here. And now I have B at its right length, and I'm going to add the arrowheads right away before I put C on place. There we go. There we go. So that's going to be my velocity of B. I'm going to copy this over, bring this down, and then put V in front of it, velocity of B. So now on the end point of my velocity of B, I am going to show the line of action of the velocity of C relative to B, which is this line right here. So I'm going to move this line, and I'm actually going to do a nearest from here and then right there. Okay. So that's going to be the velocity of C relative to B. Okay, just a label right now. And then the last one, if we go back to, so we did the right-hand side of our equation here, we have VB plus vectorially and only the line of action for C relative to B. Now we're going to cross over that equal sign. So we're going back to the origin and we're going to show the line of action of C. So we know C can only be horizontal, right? So we're going to move this line from over here to there. Okay, there's its line of action. So now we can see that there's going to be an intersection right here for these two. Add my label right away. So I'm just going to copy this. Let's see. Okay, and I'm going to use that fillet function again. Okay, you could do an extend. So there's the trim and the extend. So you could do the extend here and then trim away the extra. Or I'm going to do an undo. Like I said, you can do the fillet command because it has a radius of 0 if you haven't changed it yet. And then we would trim away this part here and then add the arrowheads. So since this is a vector or a velocity of B plus vectorially C relative to B, those arrowheads for C relative to B are going to be right there and here. Okay. And then we go back to the origin. So the tail of the velocity of C is going to start at the origin and its tip is going to go to the last arrowhead on the right-hand side of the equation. We are going to go like that. Dylan, did you have a question?
Yeah, is there a quarantine number?
I don't know. That's the fillet with a radius of 0. Yep. Okay, so now, as we look back at our problem has velocity of C, and we just want to know, what is its magnitude and which way it's going. We already know it's going to go to the left. So to find out its magnitude, we're going to go back here and we're simply going to dimension the length of vector C. So I'm going to go on my notes layer. I'm going to go to linear dimension here to here. And it is 2.725. But remember, we drew this to a scale, right? Instead of drawing the vector or the velocity of B 371.69, we did it at 3.71. So the actual magnitude of velocity of C here is going to be what? 272.5, exactly. So if we go down here, our final answer is going to be 272.5. And what are the units? Inches per second, exactly. Now, to show this work, you will need to show me any calculations that you do here, okay? But then you can use screenshots of the work that you do here. So I would probably move this nice and close, kind of right there. And for handing in purposes, I want to see that you did it in CAD. I want to see your vector diagram, but now you can do a screenshot like the Windows Shift S or the screen snip function, and then you can add it into a document where you would then also show your calculations. Now you can show your calculations in hand form, okay, in manual form if you would, written out like this, as long as I can read them. Some students will put in and type in, the work here. That's up to you. I don't expect you to take that extra amount of time, but you do have to show, your final answer in the final form and show me the process that you go through, including snapshots of the CAD work that you do that's labeled so I can see what you did. Okay. So any questions? So today we really looked at problems that are going to be using relative velocity method graphically for like crank and rocker type of applications, and also crank slider applications. At this time, do you have any questions in regard to the work that we've looked at so far?
Yeah, I was gonna, so you changed the, what was that, for a second, you changed the, what, you changed it by 100 divided by 100%?
Correct.
Why do we do that again?
Well, if we go back and we look at the illustration, this is only drawn to 2 inches long. If I would draw this 371 on the same document, the same file, that vector diagram would be huge compared to my my kinematic diagram. So to make it more proportional, so I could do a single screen snip, I did it like this.
Oh, you scaled it just so it could.
Yep, I
Okay.
scaled it just so that they could be like right there. If I wouldn't do that, then it would be huge compared to, and then I'd have to, you know, adjust all of my labels and all that kind of stuff. So I just tried to make it so that it was closer to the size of the actual kinematic diagram. But then my final answer is not 2.72. My final answer is 272.5.
You also corner it though anyway, so even though you scale that distance, it goes away when you end up cornering it, correct?
Cornering it.
So like, cause you're saying that you scale it so it fits, but I'm saying like, if you left it super big and you trim it up at that, the big part's gonna go away, isn't it?
Okay, I drew mine, like my vector right here, the velocity of B, I drew it physically at 3.7169 inches long. The actual vector would have been 371. So if I draw a line, and I'm just gonna draw it, I'm gonna draw it, I don't know, down and at an angle like this. So this would be 371.69, okay? I would have to do I mean, this is so small compared to the actual length. So I divided that number by 100 so that I could show it side by side. But my final answer has to be multiplying it by 100 again with the correct units. Does that make sense now? You could do it like this, but then you would be doing separate screenshots for each one. I just wanted to kind of put mine right next to it. That's all. So that it wasn't, the diagram wasn't super small compared to the vector diagram. Some of them, you won't have to do that. Others, you may have to, okay? So it's a personal choice how you want to show it. I just tried to make it so they were on the same diagram. And now I have one screen snip as opposed to, you know, 2, if you would. Does that answer that question, Dylan? Okay. Anybody else have any questions of the process wise that we went through? Okay. All right. Oops, I see one in the chat here. Hold on. All good here. Okay, good. Good. Then I'm not done for the day, but I am gonna stop this particular video right here. Okay. And this is gonna kind of like round out, if you would, our lecture on the process for relative velocity stuff. And then now what we'll do is we'll start looking at the homework problems, but I want to do those individually. So then you can always go back to those individually if you need to, okay, rather than lumping them into our full lecture. Okay, so I'm going to stop for this one.